Okay, hello everyone. So let's start for today's class. Yesterday we had seen about switch logic, okay, and and basically switch logic is based on pass transistor and transmission gate logic, okay, and then we saw about the pass transistor logic, okay, and basically a single NMOS or a PMOS can be used as a pass transistor, okay. So the input is provided at the drain, uh, and the output is taken at the source end of NMOS pass transistor, okay. And there would be one controlling signal provided at the gate of the pass transistor. And we had seen the operation of this particular AND gate using NMOS pass transistors, okay. Then this XOR gate we had seen, okay. Then but there was a problem there that pass transistors cannot be cascaded by connecting the output of a pass gate to the input of the next gate, okay, because there is a degradation in the output voltage as compared to the input voltage, okay. So it becomes very difficult to cascade many number of stages as far as pass transistor logic is considered, okay. And also I told that it can be overcome with the help of another the next topic, that is transmission gate logic, but that may not be completely true, okay. So take note of this point, that okay, transmission gate is better as compared to pass transistor logic, okay, in terms of uh, uh, passing the input voltage to the output voltage, okay. But there is a small problem that you may not be able to we may not be able to cascade a large number of transmission gate stages also, okay. So take note of this point, okay, because in the previous class I told that this may be overcome completely with the help of transmission gate, which is not completely true, okay. And we will see why it is not completely true, okay. We will see what is the problem in the case of a transmission gate, okay. So let's start. uh, Transmission gate. uh, Transmission gate logic, okay. And as I told in the previous class that uh, and this is also important point, that and also a limitation of the pass transistors, that NMOS uh, is good at passing strong uh, 0, okay. And whereas PMOS passes a strong 1, okay. So both of the activity cannot be done by NMOS or PMOS alone, okay. Whereas NMOS will pass a strong 0, but it will pass a weak 1, okay. And as long as far as PMOS is considered, it is good at passing a strong 1, but it may not be able to pass a strong 0. So but we need to have such circuit which is able to pass a strong 1 and strong 0 at the same time, okay, so that we can avoid that voltage degradation that is occurring in the pass transistor. So what is the solution? The solution is this transmission gate, which obviously will take advantage of both NMOS and PMOS, okay. So we know that NMOS is good at one thing and PMOS is good at another at other thing. So why not to combine these two things? Why not to combine these two fast transistors and make use of the best of the both worlds, okay. So this is what transmission gate will do exactly, that is that is it will use NMOS and PMOS both in the circuit designing, Okay, and we will see how does it uses. So basically it will so let's say one small example that we have this. Okay, we have this n MOS pass transistors, and in parallel I'm connecting PMOS pass transistor. Okay. Okay, so this is the NMOS pass transistor and this is one PMOS pass transistor, and to make use of both in one circuit, we will have to combine one NMOS with one PMOS pass transistor. Okay, then only we can use we can say that we are using best of the both of the worlds. Okay, and the input will be provided at the common input. Let's say this is the input A. Okay, and output will be taken at this terminal. Let's say this is output, maybe anything Y, F, or output simple, and let's say this is the control signal that is fed at the gate of NMOS pass transistor. Let's say this is C, and what happens that we apply the complement of the control signal at the gate of PMOS pass transistor. Okay, so take note of this point, that the control signal provided at the PMOS and NMOS and PMOS gate terminals would be complement of each other. Okay, then only we can make use of both of these efficiently. Okay, so look at this. What happens? It will work like this. If let's say if C is equal to 1, okay, that is if C becomes 1 here, that is C is 1, then C bar would obviously be 0, right? So if C is 1, then this is on, right? We know that when high logic is provided at the gate of NMOS, it becomes on, and similarly C bar becomes off. C bar becomes low, and a low voltage at the gate of PMOS will turn it on. So this will also be on. Okay, and in this case both of these are conducting. So whatever is the value of A, whether it's 0 or it can be 0 or 1, whatever. Okay, any value of A will pass directly to B. Okay, so B will become equal to A simply. A can be anything. A can be 0 or 1. Okay, so if A is 0, we know that NMOS is good at passing strong 0. So in that case NMOS will be passing that 0 completely to B. Okay, and if A is 1, we know that PMOS is good at passing 1. So in that case, when A is 1, PMOS will be in action, and it will pass the 1 logic at A completely to B. Okay, so whatever is the situation at A, it will be passed completely to B, or the output, if C is 1, right? What happens if A is if C is 1? This means that B is equal to A. Okay, what if C is 0? If C is 0, it means that this is 0. Okay, and this becomes 1. Okay, so a low logic at the gate of NMOS will turn it off. High logic at PMOS gate will also turn it off. So both of these are not conducting. So what about the situation at B? What is happening? So B is connected to what? So this B terminal is connected to this terminal and this terminal. Okay, and both of these MOS are not conducting, kind of open circuit. So So B is neither connected to 0 nor to 1, right, under this situation, right. So we say that there exists an open circuit uh, between A and B. Okay, you can also say that B is hanging, kind of hanging, or it is at high impedance, tri-state. Okay, so when C is 0, the terminal B is at high impedance state or the tri-state, or it is simply open circuit, right. It is neither connected to 0 nor to 1. So the only useful condition here, if you want to use 0 and 1 in your circuit, is this condition. It is make C equals to 1. Okay, but also in many times we would like to use high impedance state in our logic design. So in that case, we can use this condition also, that is when C is equal to 0. Okay, so this is a simple transmission gate, okay, which can be used to construct various logic gates and circuits, and we will see some of them, some of the logic gates and circuits. We will see how to use transmission gate to construct those things. Okay, and we will use symbol. There are various symbols that are there for a simple transmission gate. Okay, you will see at many a times you will see this kind of symbol where A is the input, this is the control at NMOS, this is the control signal at PMOS gate, and this is the output terminal. Okay, in various other books you will also see this kind of symbol, this one, and then this one, two arrowheads connected back to one another, and this is the input A, and here you will see C, and here C bar. Okay, and this is the output, that is B. Okay, so either use this symbol or this symbol, it's your choice. Okay, it's your choice, but as long as simplicity is considered, this symbol looks a bit simpler than this one. Okay, but you will find both of these symbols being used I think in equal proportions, and in many books I have found even this symbol to be being used more as compared to other symbols. Okay, so whatever is the case, you just you should know that this symbolizes a transmission gate. Okay, and so let's take one circuit based on this transmission gate. So let me draw one circuit. Let's say this is okay, this is PMOS, this is NMOS. Okay, and this is connected to the PMOS, and this is one NMOS. Okay, and these two outputs are connected shorted like this, and a common output is taken. Let's say this is Z output, and this is the input A, and this is the input B. Okay, and let's say this is the common, let's say this is S. Okay, and this is S bar, and this is also S bar. Okay, so this is the first transmission gate T1, and this is the second transmission gate. Let's name this as T2. Okay, so this, let's try to find out what function is this giving us, this circuit is giving us. Okay, so we have basically three inputs here, A, B and S. Okay, A, B and S, and let's go like this. Okay, we have the control signals S and S bar. Okay, and for example, look at T1. Okay, if S is 1, this NMOS will conduct, and this PMOS will also conduct. So T1 is on, and at the same time T2 is off. T2 is off. Okay, so let's go like this. Okay, so let's say if S is 1. Okay, so if S is 1, so this will make T1 on, because if S is 1, S is high. Okay, if S is 1, that will make this NMOS conducting. This will conduct. This S bar becomes 0. Okay, so this PMOS will also conduct. Okay, at the same time, if S is 1, that will make this PMOS off. This will not conduct, and this S bar will become 0, and this NMOS will not conduct. Right. So T1 is conducting, T1 is available, T2 is off. Okay, so T2 is off and T1 is on. So whatever is the value at A will pass to the output Z, and the value of B will not pass to Z. Okay, so under this condition, if S is 1, okay, Z becomes equal to the value of A. Okay, A can be 0 or 1, anything. I am not bothering about the value of A. Whatever is the value of A will get simply passed to the output Z under this condition, if S is 1. If S is 1. Okay. Now, if S becomes 0, that will just simply reverse the condition, and T1 will become off. Okay, you can verify this, and T2 will now become on, and hence Z, that output, will simply follow the value of the input terminal B, or Z will become equal to B. And again, I am not bothering about the value of B. B can be 0 or 1, anything. Okay, B can be 0 or 1, anything. So look at this condition. If S is 0, it is passing one output, and if S is 1, it is passing the other output. Okay, so if S is 1, it is passing let us say A, and if S is 0, it is passing the other output, that is B, the other input, that is B. So what is this behavior? What is this behavior? Is this a behavior of AND gate? No. Is it a behavior of OR gate? No. And what? You can easily recall that this is a behavior of a multiplexer, right? And what multiplexer it is? It is a 2:1. 2:1 multiplexer. It's having two number of inputs. The two inputs are A and B. Okay, the first input, the second input, and it will have one control signal. What is that control signal? Here, S, and depending on the value of S, okay, depending on the value of S, the input signal A or B will pass to the output, that is Z. Okay, so it is a circuit of a 2:1 multiplexer using transmission gate. Okay, so this becomes a 2:1 multiplexer using transmission gates. Okay. Okay, right. So uh, so we can have some important points regarding this transmission gate. Okay, we can have some important points regarding this transmission gate. Okay, so what is that point that it uses? So mind it, look at these points, these are important. So it is the transmission gate is using one NMOS in parallel with one PMOS. Okay, I am talking about one transmission gate. So this upper part is one transmission gate T1, and this lower part is another transmission gate, that is T2. So if you look at the structure of just one transmission gate, okay, it will be a combination of one NMOS, okay, in parallel with one PMOS. Okay, and the gate voltages, that is the gate voltages or the control voltages, control signals are applied to a transmission gate are complementary in nature. Complementary in nature, it means that if you apply a 0 at NMOS gate, then you should apply a 1 at PMOS gate, and vice versa. Okay, and it is basically acting as a switch, and actually it will act as a bidirectional switch. Okay, between input and output. So it means that the signal can flow in either direction. It can flow from input to output, and also it can flow in the opposite direction. So take care of this, because if this is acting as a bidirectional switch, then then the responsibility becomes a bit more in how to use this inside in a circuit. Okay, so basically it is using best of the both uh, worlds, that is NMOS and PMOS. Okay, that point is there, and it enables rail to rail swing. Okay, that is rail to rail swing means the output will range between the highest and the lowest possible available voltage on the chip. Okay, so it will swing between the ground and the VDD basically. Okay, it will swing between ground and VDD, and it is particularly useful in implementing multiplexers. Okay, so this is one very popular application of transmission gate, that it is particularly useful in implementing multiplexers. Okay, now for this 2:1 multiplexers, if I ask you to count the number of transistors used here, okay, so how many number of transistors used here. uh, 2 transistors for T1, 2 for T2, so 4. And we also need to generate S bar. Okay, so let's say that inverters are not available, so you will have to create inverter, and it will consume 2 transistors there. So a total of 6 transistors would be used in constructing a 2:1 multiplexer by using transmission gates. Okay, by using transmission gates, right? Okay, now the uh, the uh, we will see some more gates using transmission gate, but before that I would like to clarify. I would like to come on one point, that is called as a restoring and non-restoring circuits. Okay, restoring and non-restoring logic circuits, also called as gate restoring logic or gate non restoring logic. So as long as this pass transistor and transmission gates are considered, okay, so they are actually non-restoring circuit. Okay, so what is the meaning of this? So if some circuit is a kind of non-restoring, so it means that if input is degraded, okay, then output will also be degraded, So it means that if input signal is not perfect in value, okay, then the output will also not be perfect. Okay, because what happens here is that what is actually happening here, that we are having the pass transistors. Okay, now these pass transistors are used in transmission gate also. So let's say this is PMOS, this is NMOS, and this is input and this is output. Okay, this is A and this is B. Okay, so depending on the value of control signal, okay, we can have this transmission gate on or off. So let's say if this is on, okay, if this is on, in that case A, the value of A will directly pass to the value of to the terminal B. Okay, and whatever is the value of A, that same value will get reflected at the terminal B. Okay, it does not try to correct that value, but whatever value comes from A, it just accepts that value. Okay, but what happens in the case of a CMOS inverter? Let's say again, let me draw one CMOS inverter. Just so if this is a PMOS, okay, this is NMOS, and this is VDD, this is output, and this is input. Let's say this is A. Okay, so just to illustrate this point, at what is the difference between restoring and non-restoring circuit. So let us see at the operation of this CMOS inverter once again. So we know that Y will be equal to A bar because this is an inverter, right? Okay, but let's say if A is not perfect in value, okay, if A is not perfect, let's say if VDD is equal to 5 voltage, okay, and A is, let's say, not perfectly 5 voltage, but rather it's a 4 voltage value. So what happens in this case, that this 4 voltage will again be a case of logic high. We know that this will be treated as a logic high value, logic 1 value, and that logic 1 will make this PMOS turn off and this NMOS turn on, and in this case the output terminal will be connected to ground directly. Okay, and what will the value of y in this case? It will be simply 0. Okay, let's say another case. Okay, uh, write in another color. Let's say if a is 1 voltage, it is not logic uh, perfectly logic 0, but it's 1 voltage. Okay, again we know that this 1 voltage will again be treated as a logic 0 value. Okay, and this logic 0 will make this NMOS off and this PMOS on, and in this case now this output terminal will be connected to the VDD or the power supply directly, and that will make this Y as 5 voltage. Okay, 5 voltage, and this 5 voltage is logic 1, perfect logic 1, and this 0 voltage was a perfect logic 0. Okay, so even if the input is not perfect, but the output will come out to be a perfect 1. Why? Because the output is getting derived, the output is deriving its value, its logic levels from the power supply and the ground rails. Okay, it is not taking the values directly from the input, but rather it is taking the values from the power rails. Okay, but this is not the case in the case of transmission gate. Okay, here the output B is getting its value derived from the input directly. So whatever is the value of A, let's say if A is 4 voltage, that same value will get passed to B and it will become 4. It will not become 5. It is not making it perfect. It is not doing any corrections in the output value, but whatever value is coming from the input side, it is just accepting that. Okay, so this is the difference between restoring and non-restoring circuits. So the CMOS inverter is a case of gate restoring or simply restoring circuit. That is, it restores the value of logic levels at the output terminals to the perfect level at VDD or 0. Okay, but this transmission gate and pass transistors are non-restoring in nature. It does not correct the output value to the perfect logic 1 and logic 0 levels. Okay, and because of this, again because of the fact that transmission gate are non-restoring in nature. Okay, and so this again puts a limitation in how many stages we can use in series by using transmission gate. Okay, when using transmission gate. Okay, so this puts a limitation in making cascaded connections. Okay, although this is better than that pass transistor in the sense that the limitation of individual NMOS and individual PMOS is getting eliminated, but still if somehow the input gets degraded, okay, then output will also get degraded. It is not restoring the input imperfection to the power rail values. So this thing is not being done at the transmission gate circuits. Okay, and this is being done in CMOS, in the CMOS logic design style. Okay, so this, because of this will put a limitation in how many series connections can be done, because if we assume that the input signal is degraded, then the output will also be degraded. Okay, so only under the assumption that input signal is a perfect in value, then only we can use this transmission gate to construct a series, many number of series stages connection. But we are not sure about this. Okay, we cannot be sure about this, that whether the input value will be perfect in level logic levels or not. You cannot be sure about this at each time. Okay, so what is the point here? That okay, transmission gate is better as compared to pass transistor logic in terms of its operation. Okay, but it is still there is still a certain uncertainty that we cannot use this in making a long series connection. Okay, so although it makes some improvement over past transistor, but there is still some limitation which cannot be overcome here. Okay, and also it will consume more number of transistors as compared to pass transistor, because here for each transmission gate we are using 2 pass transistors. Okay, so this will consume more number of transistors as compared to pass transistor logic. Okay.